Hello everyone, welcome to the tower. Thank you for watching this new episode of the tower Beyond the Future. Now it's 2 minutes past 2 p.m. in New York is 8. It's 3 minutes now past 8 in Central Europe, is 3 past 7 in the UK, and it's 3 past 11 a.m. in the Silicon Valley, in Seattle, and in the west coast of the US. Thank you for all the people watching this video from any part of the world. Today we are going to speak about another innovation that is going to transform the world that we see today in the next months and especially years. So we are going to see edge technology. We are going to speak about soft robotics. So soft robotics is the first step to cyborgs. And in the past video, I recommend you, if you didn't watch the video number 3 about digital twins, I recommend that you watch it in the channel, in the tower, because we spoke about transhumanism. So we are going in a way to evolve ourselves, our bodies, to integrate and to combine with the technological gadgets and new technologies, artificial technologies made by us that will enhance our skills and will enhance our intelligence, our maybe the possibilities that we can do with our own body in the physical reality. And today we are going to speak about this again. We are going to speak how we are going to evolve to a kind of cyborgs in the future, and not so far in the future. Probably you will see people in the present that is almost a cyborg, is half human, half machine, not so half, but a share of of his or her body is artificial. And this has a lot to do with soft robotics. So first of all, what is soft robotics? Let me go to the first slide and let me put it in full screen because it's very important that you see what is a soft robot. So a soft robot is basically a robot. Everyone knows what is a robot. I don't need to explain that. But the difference between a traditional robot and a soft robot is that the latter, the soft robots, are primarily composed of materials with elastic modules that are very similar. They behave very like to the human body or to biological materials or to soft tissues. You may name it as you want, but the idea is that we are used to hard robotics, so we are normally in the traditional way of manufacturing robots. They are made by steel, by iron, hard materials, maybe plastic, but it's rigid plastic, and we are used to the traditional robotic arms, maybe the androids, the humanoids that we see. Elon Musk is producing a humanoid robot. We have Asimo in Japan, made by Honda some years ago. All these robots are hard robotics, so they are rigid pieces that move normally by small motors, and you see limited movements and some difficulties to interact with the living bodies, the nature, because nature is soft. You usually have to deal with a lot of soft materials during the day, and your body itself is soft. So nature is soft normally, only dead things are hard. Stone is hard, earth is hard, but the living bodies and food and most of the materials that we deal today with are soft. So to manage that and to provide useful value to our daily lives, soft robotics play a major role. And we find some examples here. These are prototypes, obviously. There are not commercially available solutions today for soft robotics, but you can see, for example, number one is a soft robotic tentacle. So it's like an octopus, but it's made of a soft plastic that moves with a robotic algorithm. So you can do different things with this kind of tentacle. The second picture, number two on the right, is a swarm. It's a robotic swarm. It's or a snake. We can call it any way. But the idea is that these forms are very efficient doing certain tasks. For example, when exploring pipes or even in our blood in our blood system, we could implement these micro worms or micro snakes exploring our body inside from the inside. So a lot of applications for this new robotic approach. The third one is more famous, because you probably, if you look for videos, robotic fish is very famous, and it has some years. This prototype is a soft robot that has the form or the shape of a fish, so it can swim under the water by moving exactly like a fish, and is soft. So the movement is also soft. Number four is another kind of snake. In this case, is multi-activated by small pipes, small tubes. You can see different connections. So is a laboratory prototype, is useless. And number five is also very famous because it's like an X. It's like the letter is an X that is inflated by air, and it can move. So the different ends of the letter of the X or the cross, you may name it, they move like an insect or like a spider, or is a very basic movement. But it demonstrates also that with soft tissues, with soft materials, you can do movement and you can make some force as well. So regarding force, number 6, let me put it full screen again because it's very important. This is a major achievement. This is also a prototype, but it's like a ball. It's quite weird hand, robotic hand. So you see in blue, like a glove that is soft and can grip a glass, a crystal glass. So it's very fragile and can handle it with a lot of care to pour the liquid very precisely. And this is important because the major problem of soft robotics is about how strong can be a robot that is inflated by air or by liquid. And there's been some advances in science and in technology regarding that. Let me show you something about these challenges. So before that, I chose to put two additional pictures because they are funny. So you can see on the left, you can see a soft robotic grip in a factory that is in charge of handling donuts. So this is something that is done already in many factories. So it's minimal soft robotics. So it's just the final part of the grip is made of gum or plastic or flexible plastic, and it can grip a delicate item like a donut or a cake or whatever. In the second picture, the large one, you can see a soft robotic hand. It's connected still to a hard system, a still rigid arm, but these soft fingers can manage delicate and sensible and fragile items like fruit in this example. It's still in the laboratory stage. So the challenges here for soft robotics, and they must be solved in the next months, and they are being solved for the latest years, and we will see some prototypes in the very near future. It's how we move these soft robots, because normally, robots, let me show you my hands. Normally a robotic arm has what they say the elbow or the winkle or whatever articulation. So articulations are here, here, and that's it. So everyone else is rigid. In our body in itself, there is a skeleton that is rigid. So we only move certain parts of the body. We don't move, our arm is not fully flexible. So this is the challenge. How do we build robots that combine a rigid skeleton or some rigid parts with some flexible parts that are managed by air or by some liquid, the same way that we the living animals have. So we are liquid in the inner of our body. We are almost liquid, and this is the challenge. And there is also another challenge regarding materials, because the problem with managing liquids and managing air is that you may guess. So we are inflating and deflating or putting some pressure with a liquid in something that is a bag. This is a capsule, or maybe it can behave like a balloon, so it can explode. There is limitation in the pressure that this part can do. For example, if you use a glove, you can inflate a disposable glove that is typically used in hospitals, for example, but this glove will not be able to grip a heavy load. So maybe something that is very light can be managed by this structure, but you for sure will not be able to handle a book or even heavier instruments. So this is another challenge: how to manage the force with the soft hands or the soft elements. And another point that is very, very important is how do we print the soft robots in 3D technology, 3D printing technology. Why is that important? You may ask. Why it's that important? Because in reality, in the robotics industry, normally there is a manufacturing chain and there is no need to print in 3D. In soft robotics, this is very important because soft robotics have a major application, a top priority application in healthcare to be used as prosthetics. Okay, so for people without hands or with a problem in their body, a movement problem, a disability, and everyone is different, and every prosthetics is made ad hoc for this person. So we need to use a 3D printing process because we cannot afford a mass manufacturing for building just one item for one person, and this is relevant as well. And the final point is how will robots succeed in the intended environment? What does it mean? The idea is that soft robotics have a lot of applications, so they can be applied to prosthetics. They can be applied in medicine, in healthcare. They can be applied in manufacturing, like the picture on the top left of the screen. They can also be applied to space exploration, because there is a problem in space exploration. We need to manage things. When you send a vehicle to the moon, for example, or to Mars, you don't know at first, in the first moment before you send the robot, you may find surprises there. So a soft hand will be much better than a typical steel hand to collect samples or to dig or whatever. So it's interesting, and also soft robots are, maybe they are weaker in the sense that they cannot handle heavy loads, but they are more robust because soft tissues, soft materials resist impact better because the impact is distributed better on the surface. So the impact in space, there can be impacts on the landing or whatever, and it's better. So it's important to analyze all the use cases of soft robotics for the different industries. And this is something that is still being done in laboratories. So that is the reason why we can see, if you go to a lab facility that is working on soft robotics, you will see incredible things. You will experience technology of the future, but that is working today, but only in laboratories. Why is that? Because the translation to the real environments takes time, and they need to be tested, and they need to be implemented and adapted for all the use cases that we can find once the technology is ready. Okay, so how do soft robots work? What is behind, or what is inside a soft robot? Let me put this large again in full screen. So we have mostly two approaches. The left side of the screen shows the classical approach. So you have some chambers that can be filled, chambers or channels or tubes, pipes, whatever, that can be filled in with the liquid or with air or with gas. It depends. Okay, so gas material, liquid material, water, oil, whatever. This is the classical approach. So once you fill in the chamber, it becomes larger and more consistent, or even more rigid. Okay, and this helps in moving the robot, or doing some pressure, or changing the shape. And this is what we play with. We play with shape, with the force, with size, and these elements. This is a classical approach. Another alternative approach is to use something called muscle wire. What is muscle wire? and maybe we will prepare a future video about muscle wires. I wrote a book some years, 6 years ago. I published a book about muscle wires, and it's an old technology. Okay, muscle wires probably have more than 20 years old, but they become an interesting technology to be applied to soft robotics. And there is very little research and very little development done on this side. So probably we will see something in the future. Why muscle wire is interesting for soft robotics? To know that, we need to know first what is a muscle wire. A muscle wire, you can see on the screen. Let me put it larger. They are wires, so you can see a lot of wires here on a hand. The interesting point of this wire is that they are made by an alloy, a special material. This material is typically called nitinol, and this material has the ability or the capability to have one size when in normal state, but if you there is a metal, okay, so the electricity can go through it. So if you pass electricity through the wire, they shrink, okay, so they become shorter and significantly shorter, okay, and this is a very interesting quality, because in nature normally when you pass electricity the wire hits, and when something hits it spans, so it makes the wire larger, but very little, okay. You don't normally when you plug a wire on the outlet at home, the wire doesn't change too much, you cannot perceive it. But in muscle wires they shrink, and they shrink noticeably. So they shrink probably a 20 centimeters wire can shrink to 18 centimeters, can shrink 10% or maybe more, 15%. Okay, and this is interesting because this way a robot can, this way a wire can move a robotic part. What is the essence of that? If you combine this muscle wire with the liquid, because the problem with muscle wires is that they shrink and they heat, okay, but if you want them to return, to get back to the normal size, the normal length, you need to cool them, so you need liquid. So combining these structures on the left, soft robotics, chambers, tubes, channels, with muscle wires, you could build a robot or a robotic part that can have different shapes, can have high power in terms of pressure, force, because muscle wires are very strong. So when they shrink, nobody can avoid that. If you connect this wire, it's too thin, and you connect it to as rigid to two rigid ends, it will break in two. Okay, it's impossible that it doesn't shrink. And the idea is to combine these two technologies to let the grip be done by wire muscles, so strong and silent. It's important, so no engines, no motors, no turning pieces. It's just a wire that is becoming shorter, totally in silence. And then with the liquid, you don't need to do pressure. You just need to insert a cool liquid to release and to make it turn again to the original position. And this is a very interesting approach. I have to say that I haven't seen specific developments on that yet, so only literature, only theoretical approaches, but it will be interesting to see what happens in the next years. And what about materials? Okay, materials, we can use a lot of flexible materials today, but there is one material that is especially interesting for soft robotics, and this is TPU, is thermoplastic polyurethane. Why is that? Because it's a mix between gum or rubber and plastic. It's soft, is flexible, is durable, is important because soft robotics are constantly bending the material, and is smooth and can be elongated, can be pressured. So it's very, very, very flexible and feasible for this application. It can be also 3D printed. That is a very important point because not all flexible materials are able to be 3D printed, and it's stable when you apply vacuum, so they don't deform permanently. You can extract all the liquid or the air from the chamber made with TPU, and then if you fill it in again, it will expand to the regular position. It will be no deformation. Okay, so TPU is a very good material for soft robotics. But let's move forward to the interesting part. Soft prosthetics. Soft prosthetics will be the first step toward cyborgs. So we will see this kind of materials in people around us in the very next months and year, no more than 2 years, okay? What are the applications for prosthetics using soft robotics? Here let me put it full screen to let you read the different approaches. So we can find soft robotics in hands or in legs. So in the middle of the picture you have wearable robots, you have prostheses, so using it for hands. But we will also find soft robotics for assistive devices. For example, helping people in wheelchairs, adding more items, adding more elements to the wheelchair that are soft to manage, to approach or to grip different items using soft robots, soft hands, etc. Also to imitate organs, so artificial organs on the top right, we can build an artificial, for example, an artificial heart or an artificial vessel in the body with soft robotics. And also we can use soft robotic for body simulators. This is happening today, and you know it very well because of the COVID pandemic. What is a body simulator made with soft robotics? So it's called, for example, a respirator. Okay, so respirators is different from oxygen feeders. Respirator is for someone who cannot breathe with his lungs. Okay, so they put a strong tube here, and there is a machine doing the pressure and inserting the air into the person's lungs and extracting the air from the person's lungs. Okay, and this is made with a soft bag that inflates and deflates according to the shape and the size and the volume of the person's lungs. So it's configured to behave exactly like the person breathes. Okay, and this is a soft robot. Is a soft bag that is moving air from the body, in the body, out of the body at certain speed, respecting the behavior, the amount of air and the precise moment, the rhythm, etc., and considering the damage of the lungs, for example, it's making precise movements of the air inside this person using a soft robot, and this is existing today, and you know it very well. And also we have here drug delivery and surgical elements, surgical devices. It's expected to do a lot of improvement in the healthcare field, because as I said before, our body is 90%, 95 or 98% soft. So if we need surgery, if we need to implement something inside our body, it's better that it's soft, because it will be much less harmless. It will do much less harm to the elements around it, and soft robotics is the number one candidate. Okay. And then this is my final slide today. What are the ideas for soft robotics? So what will we find in the next months and years, in the near future? So we have seen a lot of ideas, some from the present, some from the near future, some from the real far future, probably some years from now. What are the two approaches that we will find in the near future, in the next months, in no more than a year? We will find wearable devices. You can see them on the left. Let me put it full screen. Wearable devices are typically exoskeletons, like you can see on these hands. Exoskeletons, but exoskeletons made by flexible material, by plastic, by TPL, or by a similar material, to avoid harm to the skin, and also to provide more natural and silent movement to the body. So it will help people to move hands or feet when they can't because of a disease or an accident or whatever, or maybe they can be used to give more strength to the hand or to the body, for example, in military applications or in industrial applications. So if you want somebody to be able to grip, to grab a specific element with very high force, you can use this kind of wearables to increase the strength of that hand. And on the other side, on the right, we have the soft prosthetics. Okay, so we will start seeing this more and more in the near future. We will start seeing people that lost one hand or one foot or both, or maybe an ear or any other part of the body that can be replaced with a robot because it does a specific action. It will be able to be replaced by a soft robotic part, so this person can do normal life with an element that is artificial but is very similar in behavior than the original human organ or part. And this is interesting because we will start having soft robotics in healthcare, in medical applications, but everything goes from healthcare, the normal path, the normal roadmap for innovation is 99% of the times it starts with military applications. So we don't know because they are normally secret. We start with military applications. Then once it is more or less developed, they jump to healthcare Why? Because healthcare is very expensive. Normally, they solve these innovations solve problems that are very expensive to solve at that moment, and people with health problems pay a lot. They are eager, or they accept to pay what is needed to recover his life or perform a more or less normal life. So healthcare is number 2, and then number 3 is not, it was traditionally, it was the industry, the business environment, but now it's not. It's no longer valid, this approach. The number 3 is consumer. The number 3 is you and me at home. Okay, this is mass production, and we now see soft robotics in step 2 in healthcare. So they are entering in healthcare applications, and probably in 2, 3, 4 years maximum, we will see them in consumer applications, domestic applications. So we will see soft robotics being used in toys, being used in domestic appliances to help you wash your dishes or whatever. We don't know yet how many applications soft robotics will bring, but for sure this will be number 3. Considering the timing, it will be in no more than 5 years. This is my opinion, this is my personal forecast. I think it will be sooner than 5 years, probably the first applications will come much sooner, probably in 2-3 years. But for example, wearables connected with the metaverse, with virtual reality, we will start seeing a lot of things that involve soft robotics in our lives in the future. So this is my video for today. Remember to subscribe to this channel. The tower is for you. My idea is that you have a lot of videos about all the technologies that are emerging today, and this is important for promoting this channel in YouTube. So please subscribe, please do a like, click on like, to have more visibility in the search in YouTube. And also, if you have any question, please let me know. This is here, this is my website. Okay, here in this website you have a contact form, and I will answer any of your questions on the go. So I'll be glad also to hear your recommendations. If you want to speak or to listen about any specific technology, you're welcome to suggest and to propose. And also, if you work in a specific research field and you want me to interview you, please also contact me here, because I have to say that very soon we will start with the interviews. So it's very good to have candidates that are proactive. So I have some candidates now for the next weeks and months. But if you want to be interviewed and tell the world what you do in your research, in your laboratory, in your work at a university or at a research center, please contact me, and we will speak about your innovation in the future videos. That's everything for the moment. I have to say that very likely I will change the date for these videos from Friday to probably the middle of the week. It's not for personal reasons, it's just for logistical questions. I think it's better for you, for being able to watch live these videos, because I see that people watch it after they are live. And my idea is that you can participate by writing on the chat and making questions and discussing and commenting. So my idea is to move this to another day in the middle of the week. I will let you know, because I'm also experiencing with a different streaming software that is more professional, and it allows me to do more complex interactions, future interviews, etc., etc. And I will tell you, you can follow me on, you can connect with me on LinkedIn, or follow me on LinkedIn, and you can also follow me on Twitter. By the way, my Twitter account is never get used to the mirroring on the broadcast. Here you have my Twitter nickname by Antonio Flores, and if not, you can look for me on LinkedIn, and I will let you know as soon as possible. Okay, thank you very much for watching this video. Remember to subscribe, remember to click on like, and I hope that we will meet again the next week in the next video. I can anticipate you that we will continue speaking about cyborgs, this time about brain-computer interfaces and some other things, how our brain can give orders to machines directly, without our fingers, without our voice, without anything, just thinking. Okay, let's see in the next video. Thank you very much and have a very nice weekend. Goodbye.